Hello everyone, and welcome back to the AI Research Roundup. I'm your host, Alex, and today we're diving into some interesting AI research. We'll be looking at a paper called LanPaint Training Free Diffusion Inpainting with Exact and Fast Conditional Inference. So, diffusion models generate great images, but filling in missing parts or inpainting isn't always straightforward, particularly without extra training. This paper introduces LanPaint, a training-free method designed for common diffusion model samplers. It uses Langevin dynamics to perform, exact conditional inference, aiming for precise and visually coherent inpainting, even tackling challenges like slow convergence. So, the paper addresses a couple of key challenges. One is this issue of getting trapped in local likelihood maxima. Figure 2 here gives a nice visual on a synthetic 2D task. It shows these scatter plots on a probability landscape. You can see the blue dots are samples. With the standard Langevin method, especially as you reduce the diffusion steps, see those red dots? They get stuck in less likely areas, the local maxima. But look at the LanPaint plot on the left. It avoids these traps and guides the samples towards the better global maxima. This really highlights how LanPaint's big score helps overcome that trapping problem. Moving beyond the synthetic example we just saw, Figure 4 here shows how LanPaint performs on actual ImageNet images. We can see comparisons across different methods like Replace, DDRM, Langevin, Repaint, and LanPaint itself, using various masks like a center box, half the image, and even a tricky checkerboard pattern. Notice how LanPaint, both with 5 and 10 inner iterations, generally produces more coherent and realistic fillings. Especially look at the zoomed-in checkerboard results at the bottom. The baseline methods often leave visible artifacts, while LanPaint blends much more smoothly. Okay, so building on those visual examples, Figure 3 here takes us back to a synthetic task, similar to what we saw in Figure 2, but this time focusing more broadly on accuracy. You can see the ground truth distribution shape in the top left plot. Then we have results from a whole bunch of methods: Replace, DDRM, Repaint, Langevin, and of course, LanPaint. What's really telling here are the KL divergence scores. Lower means better accuracy. And LanPaint, especially LanPaint 10, clearly gets the lowest scores, showing it reconstructs that distribution much more faithfully than the others. Okay, so shifting gears slightly, Figure 7 gives us another set of visual comparisons, similar to what we saw in ImageNet, but this time using the Saliba HQ dataset, which is focused on faces. Again, we see the original, the masked image, and then results from various methods, including LanPaint 5 and 10. Across the different masks, you can really see LanPaint producing, more realistic and coherent faces, especially compared to some of the blurrier or artifact-heavy results from other methods. Look at that checkerboard example again. LanPaint just seems to handle it better. Now, Figure 9 takes this a step further. Instead of just filling in masked areas, like we saw in the faces and ImageNet examples, this figure shows prompt-guided inpainting using stable diffusion. So they're asking the model to fill the masked region with specific things, like an ocean, or mountains, or a forest. And again, if you look across the results, LanPaint seems to produce the most visually coherent and semantically aligned images that really blend well with the original context, avoiding those weird artifacts or mismatches you see in some of the others. So wrapping up, what we've seen across these different examples, from synthetic data to real-world images and even that prompt-guided inpainting, is that LanPaint really stands out. It delivers highly accurate and visually compelling results without needing specific training for the task. This kind of exact and fast conditional inference is a significant step forward for diffusion models, especially for image editing applications. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.